All right, this is I guess it's part two of my research into building an end-to-end encrypted messaging system using Bitcoin Cash and the interplanetary file system. So, where do I start with this? What I'm going to do with this video is I'm going to give a prototype demo of a permissionless, uncensorable, end-to-end encrypted messaging using IPFS and Bitcoin Cash. And this is an extension from previous videos that I've put together. So let me give a quick bit, before I get into the demo, I'm going to cover a bit of the background because this has been an unfolding amount of research and narrative. There have been people involved. There's a lot of interest in this technology. It's very salient given the times that we are in and the times that we are going into, and I'm going to cover the why of why end-to-end encryption is so important, and sort of the macro forces involved. So if you are seeing this for the first time, or you just want to get to frame what I'm about to say, I want to give a little bit of the background. So the way this got started was an initial video that I published for a piece of software that I called BCH Encrypt. And if you go to my YouTube video, I have this YouTube video, Encrypting Messages on the Bitcoin Cash Blockchain. And I don't want it to play, but this is the first video where I gave a demo of this software right here, BCH Encrypt. So if you want to see the code for that in that video, you can go to github.com/christroutner/BCH Encrypt. And this was a prototype using end-to-end encrypted messaging and only using the Bitcoin Cash blockchain. It took the elliptic curve encryption that's baked into Bitcoin, the Bitcoin protocol, and it showed how to chunk up a message, encrypt a message, chunk it up, write it to the blockchain so that you could retrieve it using member.cash or member.cash. And then as a result of that video and this demo and this code, I was interviewed by Edward Kelso at CoinSpice.io, and here is the page with the podcast. And I really had a lot of fun making this podcast, so this is just pure entertainment. If you're not technical, this is fun. This will help capture like the issues around the Earn It Act and other acts that have tried to stomp on our rights to free speech and rights to privacy. So this is a good, entertaining way to do it. The code, the prototype I built, has since been integrated into member.cash. So if you create an account on member.cash, you can go to this little icon here with the E, and that's going to take you to the encrypted messaging. So this is using the code that I wrote, and you can see these are actually private encrypted messages that people have sent to me. And what it does is it lets you find another person on member.cash or memo.cash and get their Bitcoin Cash address, and then encrypt a message that only they can decrypt with the private key associated with that Bitcoin Cash address. So what I'm going to do today is extend this, what I started there, and show how to use IPFS and discuss some of the pros and cons of combining IPFS with Bitcoin Cash in order to build a better end-to-end encrypted messaging system. And I'd really like to do an interview with Naomi Brockwell on some of these subjects. So hint, hint, Naomi. I'd love to be interviewed by you, and you can find some time and sort of take this to the next step. Kelso did a great job of helping me zoom out and tell the narrative in terms of the current political climate and some of the past threats, and just help me get the message out to a less technical audience, and I could use help with that. So let's speak to that right now. The reason why I'm so motivated to come up with a good end-to-end encrypted messaging system is that what I see happening right now in 2020 reminds me strongly of what I saw happening in 2008. And Bitcoin was born in 2009 as a result of the Great Recession, And as also in parallel to that, there were a lot of protests and revolts, and people organized their protests using Facebook and Twitter, and we saw massive amounts of censorship on those platforms by state actors in order to combat the protesters' ability to organize and communicate. And in the last 12 years, state actors have gotten much better, much more efficient at censoring and disrupting communication on those large platforms. So we really need a peer-to-peer, uncensorable communication medium for the protest and revolts that I expect to see play out over the next year or two. So that's what I'm trying to do, is I'm trying to build these tools that those people are going to need in the near future. And that's why I think it's important. And so that's the why. So let me show you a flowchart of the way this works. So in the past, in the previous example, used only BCH. So what's new in this demonstration is I'm now using IPFS. So here's a flowchart to help explain what's going on, because there's a lot of moving parts. But basically, Alice wants to talk to Bob. She wants to send him a message that is encrypted and private and that cannot be censored, cannot be stopped. So maybe Alice is in China and Bob is in Iran or America or whatever. Like, pick a country that typically doesn't like members of that country talking to other members of another country. That's the problem that this solves. And so here's a flowchart of how the communication would happen with this new prototype that I built. So and also, so I have these columns: the internet and Bitcoin Cash and IPFS. So BCH is Bitcoin Cash, IPFS is the Interplanetary File System. These are all separate networks. Most people are familiar with the internet and they think that, like, oh, the internet's it. Or actually, this should really say web, because the internet encompasses all of these, if I'm being technically correct. The web is not the internet. The internet is all of these things. So this would be more technically correct if this said the web. But what I want to point out is this column with the internet. There's only one block in this column. The internet is almost not used at all in this scheme. Instead, this uses Bitcoin Cash and IPFS, which are two peer-to-peer technologies that do not rely on the web, and they can't be censored using the same tools that state actors use for censoring content on the web. And I mean, the obvious ones are like Facebook and Twitter and YouTube. Those are actively running censorship campaigns. But also, like, just the more general censorship of, like, taking a website down, which is more difficult, but is still done. Those techniques would not work to combat or censor this type of communication medium. So let's just walk through this flowchart real quick. Okay, so Alice wants to talk to Bob, and she wants to do it privately and uncensorably. So the only part that the web is used is to find Bob's Bitcoin Cash address. Let me give you an example of how someone could do that really quickly. Again, using member.cash. If I go to the home page, let's see. Okay, here's Super Hacker. Here's a message from Super Hacker. I haven't seen this before. I don't know what it is really, but I can click on his profile, and here's his Bitcoin Cash address right here. And you can do the same thing in memo.cash. There's Kieran. Here's Naomi Brockwell. Let's say I want to send her a message. I can go to her profile, and her Bitcoin Cash address is right here. So that's the only piece of information that I need in order to send her a private, uncensorable, encrypted message. So someone does that. They find the other person's Bitcoin Cash address that they want to use to communicate. And then, so this is where the demo comes in. The demo I wrote would retrieve Bob's public key from the blockchain, and then it would encrypt Alice's message with that public key. And then, instead of the previous demo, which wrote the message to the Bitcoin Cash blockchain, it would instead write that encrypted message and upload it to the IPFS network. And then this Alice's all the software is happening in Alice's wallet. Alice's wallet issues a transaction to the Bitcoin Cash blockchain that signals to Bob that he has a message waiting for him. And so then when Bob loads his wallet up, his wallet's going to scan the transaction history for his address, and it's going to locate the signal, and then it's going to use the information in that signal to go and download the message from the Interplanetary File Systems Network. And then it'll decrypt it, and then he can access the message. And so it's peer-to-peer, and it's encrypted. So that's the basic flowchart of how this all works. So before I jump into the demo itself, let's talk about IPFS and BCH and what the pros and cons are of these different mediums and ways we could use them. So some of the things that the Bitcoin Cash blockchain, and so I'm focusing on Bitcoin Cash. This could be done on BSV. I don't think it could be done on BTC, the Bitcoin Core. So just keep that in mind. I'm just focused on Bitcoin Cash personally. And but both, so Bitcoin Cash and IPFS share some similar qualities in the data, in that there's a strong immutability. So once you write data to the blockchain, you can't change it. And same thing with IPFS. Once you write the data, it gets a hash, and that's immutable. You could change the file and re-upload it, in which case you'd get another hash. But there's strong guarantees for immutability, and to put it in a more like English-speaking format, that also means that there's a strong cryptographic guarantee against tampering. So if you upload a piece of content to IPFS, you have a strong guarantee that no one has tampered with it, because if they changed even one bit, that hash would change. And you get a similar guarantee to the Bitcoin Cash blockchain, because that data is immutable and verified by all the peers. They're both highly censorship resistant. So in Bitcoin Cash's example, everybody has a copy of the blockchain and they maintain it, and that's how everybody stays in consensus. And so if you tried to censor any piece of content, the network would simply fail to work. And so by the fact that the network is working, you know that no one's censoring content. And then in IPFS, they have this amazing piece of tech under the hood called libp2p, which is just incredible at sneaking around firewalls and connecting nodes and just making the whole thing work. And it's very, very difficult to block IPFS nodes. And both technologies are peer-to-peer. They don't rely on some center server that can act as a bottleneck. People can run these software on their computer and connect peer-to-peer without any person or server in between them. So what's some of the pros to writing to the blockchain? One big advantage of writing to the blockchain is the content is guaranteed. Anybody who runs a full node has a copy of the blockchain. Everybody's sharing the same content, so the content is available. So there's these two problems that you have to solve when you want to send someone a private message. You have to make sure it's private, which is where the encryption comes in, but you also have to make sure that you can get the message to the recipient. And the blockchain's really good at that, because you know that they'll be able to get the content. IPFS is much more efficient at delivering content, and one of the trade-offs they made to be so much better at that is that the content's not necessarily guaranteed. Anyone can serve the content, anyone with a copy of the content can serve it, so that makes it really nice. But if no one actually has the content, then no one can serve it. The content is not necessarily guaranteed to be available. Another advantage of using just the blockchain is that you have a single communication medium. And I've had long talks with Vin Armani and his swap protocol. He wants to keep everything on chain, and one of the reasons for that is that it makes everything much more simpler when you're just using a single communication medium. And I have to agree with him on that. That is a really good reason to just put everything on the blockchain. But there are also cons to putting things on the blockchain. So let's explore that. just like the content is guaranteed to be available, that's a double-edged sword, and it cuts both ways. Any piece of content you put on the blockchain cannot be deleted, and it's there forever. So all the like frivolous messages on member.cash, as much as I love them, they're there in the blockchain, and they'll always be in the blockchain, and whatever we do in the future with the blockchain is going to have to include that data. And so that's again a double-edged sword that cuts both ways. And so this blockchain bloat is not something I spend a lot of time worrying about, but it is something that any serious technologist in working with the Bitcoin protocol has to keep an eye on in terms of long-term goals and feasibility. And so large messages are prohibitive, and this is really starting to get at the core differences between BTC and BCH and BSV, where BTC made the blocks small, BSV made the blocks really big, and BCH, I feel, made the blocks just right. So the fact is that putting large files on the blockchain is prohibitive for several different reasons. And so that's another good reason not to write content to the blockchain. By doing it this way that I just showed in that flowchart, you can send encrypted messages or encrypted files of any size. There's no ceiling on the amount of size of the file that you can send, like a video file or a music file or a text file or any type of file. And IPFS is really, really efficient at moving that content around, like much, much more efficient than the blockchain is. And so a big advantage of doing it this way is scalability. And it gets around I feel like it strikes the right balance between the pros of writing like a single signal message to the blockchain and the cons of trying to like write large pieces of content to the blockchain. Okay, so with all that background, let's jump into the code. In fact, I thought I had another graph here, but yeah, let's jump into the code and do this demo. So whereas before the first demo was this BCH Encrypt program that lived on its own, I needed more of a full-featured wallet for this part of the demonstration, and it takes advantage of some of the newer features at fullstack.cash. So let me just talk about that for a minute. So fullstack.cash is a blockchain as a service that I've built and I'm offering. It's a subscription service where it gives you access to the REST API so that front-end developers can build apps to interact with the Bitcoin Cash blockchain. So phone apps and web apps. If you're a front-end developer and you don't want to worry about all the back-end details, of which there is a lot, you can just pay $30 a month, get a key, and then you can hit the ground running and just focus on building business solutions and not get bogged down with all the intricacies of running an SLPDB database, an Electrum X server, and a REST API, and maintaining a full node. So that's the value that it offers, but I actually just added this IPFS pinning service at ipfs.fullstack.cash. So you can grab a file and upload it. Now this is the front end. There's also a REST API. Let me show you that. That's at ipfs-api.fullstack.cache. And this is the REST API documentation for interacting, particularly the files. It shows you how to create a file, upload the file, or create a file model, upload the file, get all the files, and get a file by its ID to check on the status if it's been updated. There's also this nice front end. So I uploaded the file, and now it's saying send this much Bitcoin Cash, which is equivalent of 1 penny, to this address to pay for the hosting, and the file will be hosted on the IPFS network for 30 days. And then it will be automatically deleted, which I look as a feature. And this is an alpha. I'll add more features, but just sticking with this for a minute with some of these new features, I also added, if you go to the documentation page, so if you go to fullstack.cache, scroll down to documentation, you can find the API reference for BCH.js, which is the JavaScript library, and BCH API, which is the REST API. So if you're a JavaScript developer and you want to use the BCH.js library, I've also added the IPFS, same REST API endpoints are baked into the BCH library, so you can create a file model, upload the file, and then get the status of that file. And that's not it. That's not all. If you go to, again, the fullstack.cash homepage and go to the examples, there's a link to this examples repository on GitHub. And if you go to applications, there's a new IPFS folder. And here are quick start examples of how to use BCH to go through everything that this demo goes through, which involves uploading a file, paying for it, getting the IPFS hash, which is what you use to retrieve other people would use to retrieve the file from IPFS. And so make sure and walk through some of these examples if you want to get started doing things similar like what I'm doing here, which is uploading data to IPFS, which I feel is a very excellent complement to the Bitcoin Cash blockchain. Okay, so that's some of the new resources that I've put up, and that's what's going to be happening under the hood. The demo I'm going to show is it's in SLP Cli Wallet, which is a full-featured command line application that is an HD wallet, and it works with SLP tokens. And so I created a branch called Encrypt. So the way to get to that is right here, this drop-down box. You'll see an Encrypt branch there. That gets us into the Encrypt branch. And then if you go into the commands directory, this is where these new commands live, which is decrypt message and encrypt message and get key and set key. And that's what I'm going to show how to use right now. And just a quick note, if you've never played with SLP Cli Wallet, the way to install it is not this way. You want to follow these instructions, where you clone this repository, npm install the dependencies, and then you can execute the commands like that with a /bin/run. So that's what you'll see me doing. Okay, so let's get into the demo. Okay, so here I am in SLP Cli Wallet. I've already installed my dependencies. I have quite a few wallets. In fact, I'm going to delete some of my old wallets. Okay, so I'm going to create a new wallet. Bin run create wallet Alice. So actually, let me walk through this. So if you go help, that'll list all the commands that this application can do. So if I go bin run help create wallet, these are the commands. I'm so familiar with this, I'll probably go pretty fast. But if you are wondering what these different little dash letter arguments are that I'm using, this is the way you can get information on them. So I'm going to create a wallet named Alice, and I'm going to create a wallet named Bob. And I'm going to use this new set key command, which will create a key pair that I'll use for the messaging, which is very similar, same idea behind member.cash and member.cash. They use a key pair, and so let me just show you what that looks like. Bin run set key Alice. Need to say in. Okay, cool. So it gave me a Bitcoin Cash address, the simple ledger version of that if I want to send tokens to it. This Bitcoin Cash address is displayed as a QR code because I'm probably going to need to send money to it. Here is the private key in with format, and then here is the public key, which this is used for encrypting the messages. So what I'm going to do is I'm going to send a little Bitcoin Cash to this address. I have a wallet called Trash where I just put stuff, Bitcoin Cash when I'm done using it. I'm going to send it to this address, and I'm going to send 20,000 Satoshis. This is this SLP Cly wallet. If you use it, you may end up getting messages that like, you need to increase your rate limits. This is a tool for people who subscribe to the fullstack.cash services. So it's right here under on the examples page is another way to get to the code, and you'll wanna read about the jot handling. I have a jot token which allows me to use this wallet without getting stopped because I have increased rate limits through fullstack.cash. Okay, so I funded Alice's wallet. Let's also set the key with Bob's wallet. Let's see. Set key, Bob. And so I'm going to send the same amount of Bitcoin Cash to Bob's wallet. Now, in order for Alice to send Bob a message, she needs to be able to get his public key, which is this right here. And unless Bob gives it to her explicitly, like you would say in an email situation, which is a huge source of friction, as long as Bob has made one transaction with this address, we can automatically retrieve that public key from the blockchain. And that's a huge feature, and I think a huge advantage over typical email encryption, where you don't have to have someone give you the public key, or you don't have to search a database and try and find someone's public key. You can just automatically get it from the blockchain. And that is just, it's hard to emphasize how awesome of a feature that is. But again, Bob needs to make at least one transaction. So what I'm going to do is I'm just going to, the funds that are now in Bob's wallet, I'm just going to send it back to itself, and that'll create the transaction needed. Now, normally, if we were using this in a social media situation, and I use, say, Naomi Brockwell's public address, she's already made a bunch of transactions simply by posting to member.cash, so that information's already there. But these are brand new wallets that haven't existed before, so I need to do that. So I'm going to send all. I'm going to ignore any tokens, because I know there aren't any, and I'm going to send everything in Bob's wallet back to Bob's wallet. So this is just generating the single transaction. There needs to be at least one. That now Alice's wallet can go and get Bob's public key. And so this is like one kind of little caveat, but it's really not a big deal in practice. Okay, so now we're all set up, and let's go back to the flowchart. So Alice needs to find what. So first of all, let's encrypt the message and upload it. So there's two parts to this. There's the encryption part, which ends right here. And then there's the decryption part, which is this last half. So let's do that encryption part. So we're going to go bin run encrypt message. Okay, there's the description and the command. So we're going to use Alice's wallet, and we're going to send it to, oh yeah, so what was Bob's? Let's get Bob's. Bin run, get key, Bob. Okay, that's Bob's information. Send, encrypt message, Alice for Bob's address, and we're going to send a message. This message is encrypted. Isn't that cool? Okay, that's the message we're going to send. Okay, so it went out, it just found Bob's public key. You can see it looks just like that one from the blockchain. Now it's encrypting the message, and it has uploaded it to the IPFS pinning service at fullstack.cash, and it takes about 2 minutes. So it uploaded it, it got a file ID, it got a Bitcoin Cash address to pay, and an amount to pay, which is 1 penny, 4,386 satoshis is 1 penny at this moment. That's the spot price. So it's already uploaded the file and paid this much Bitcoin Cash to this address, and now we're just waiting for the IPFS or the fullstack.cash pinning service to acknowledge that it's been paid, locate the file, upload it to IPFS, and then it will give us back the IPFS hash that Bob is going to need in order to retrieve the file from the IPFS network. And that typically takes about 2 minutes, so I'll pause the video and continue here in a minute. Okay, so this is the IPFS hash, and you know what, just to see what that looks like, I'll go into the code here. And we can pull it up this way. We can actually look at the encrypted file. This is an IPFS gateway. You can look at any file on the IPFS network this way. So this is the file that we just uploaded. It's a JSON object, and it has 2 properties, to address, which is Bob's address, and then the encrypted message. That message we sent, it's contained here in encrypted format. And so we uploaded that, and then so if we've got 2 transaction IDs here. So if we go to the Bitcoin Cash blockchain explorer, this first one is the transaction that we paid for the IPFS file hosting. And I just wanted to show that real quick. It's not terribly interesting. We just paid, a penny worth of Bitcoin Cash, and that paid for the file. So that's sort of like a receipt, proof that we uploaded a file. And again, we have the hash so we can verify that the file is actually on IPFS and being hosted. The second transaction is the signal that Bob's wallet is going to pick up on to know that it's that he has a message waiting for him. And it uses the member.cash protocol, so you could look at this on member.cash if we wanted to. In fact, let's just give that a go. I haven't really tried this. So if we go, how can we? Okay, well, I'm not going to worry about that then. But what I like about the Bitcoin.com block explorer is it is smart enough to look at this raw op return and look at this part and be like, oh, that's a member.cash protocol transaction, and so it automatically decodes it. And so what it is just this MSG, IPFS, and then the IPFS hash right here, which matches this same hash that we got back from fullstack.cash. And so if you look at the transaction, it's this first one this is the change. It sent the change back to Alice's wallet. This is the op return data that we just read right here. So this is the message that Bob's wallet's going to read in order to know the IPFS hash that it needs to request and get the content. and then this is a dust payment to Bob's wallet, and so this transaction is going to show up in Bob's transaction history for his address, and so that's how the software can automatically locate these types of messages, look for this data in the op return, and then it now has the IPFS hash and it can retrieve the file from IPFS. So that's the first part of this flowchart. The command we just ran found Bob's public key. It retrieved the key from the blockchain. It encrypted the message with Bob's public key. It uploaded the message to IPFS, and then Alice issued the transaction that we just looked at. So now we're going to do the second half where we actually decrypt the message. So now we're Bob, and we're going to be in Bob's wallet. And we're going to go bin run help decrypt message. Let's see. Maybe it's plural. Decrypt messages? Yeah, okay. So in this case, all we really need to do is run decrypt messages, and we're going to run it on Bob's wallet. So the prototype just finds the first message right now. Obviously this is a prototype, this is rough. Wouldn't this be great if this had a graphical user interface so we weren't so limited? So yeah, just keep that in mind. This is just a prototype, like a proof of concept. There we go. There's the decrypted message. So that command just, for Bob's wallet, it scanned his transaction history. It found that transaction. It was able to pull the IPFS hash out of the transaction, go to an IPFS gateway, and pull down this JSON object that we looked at, and then decrypt it with his private key and get the original message that we started with. So that's how it works. It's a little hand wavy looking at it like this, but again, the code is at github.com/christroutner/slp_cli_wallet, and those two commands, if you go into the source commands directory, the code for all this is in that. And then you got to go to the encrypt branch, and the code is in this decrypt messages and encrypt messages, and again there's these set key and get key commands, which are used for setting like a specific key pair for doing this sort of stuff. Just sort of mimics what naturally happens when you create an account at memo.cash or member.cash. Alright, so that's the demo, and hopefully this inspires some more people. I'd love to continue this conversation. If other developers want to help by creating a front end for this sort of thing, we could essentially create a peer-to-peer email messaging system that gets away from, email has these centralized servers. This also solves the spam problem because you're actually having to send a little bit of money. You have to actually pay for these messages, so that should prevent spam. And of course, that amount of money could be increased. If you're familiar with the Stamp project, that's what Shama Chancellor is exploring right now. Is this idea around paying to send someone messages, which is the solution to the spam problem. That could be implemented here. A graphic user interface would be great. This method of using IPFS allows you to send several files at once. You could zip them and send them as one file. You could have images and media as well as text messages. It's certainly not limited. It's not limited in size or scope of the types of files that can be encrypted and delivered. All right, so I'll leave you with that thought.